Good morning / afternoon, Year 10. In today's lesson we are going to do magnitude of vectors, but first a very important shout out to Ramis. One, because he was the person who spoke to me the most in school on Monday rather than acting like he'd never met me before, and two, because he did actually ask for one, so I said I'd do it. So there you go, Ramis. I hope that was satisfactory. Right, today we are going to be doing magnitude of vectors. So I'm going to write that title down. And there, as if by magic, the title has appeared. So magnitude of vectors. We have talked about how a vector has magnitude and direction, whereas a scalar just has magnitude. The magnitude of a vector is its length or its size. So magnitude generally means size. So we'll write this down. The magnitude of a vector is its length. We've talked about the magnitude of numbers. For example, if we have the number -3, its sign is negative, but if we take the magnitude of it, that is the size of the vector, the size of the number, -3 is 3 away from 0. So the size of -3 is 3. In the same way, we can have the size of a vector. So if we have vector P, and that is made up of its x component and its y component, then the magnitude of P, so same symbols as we use for the magnitude of numbers, is the magnitude of P. Now this vector P, let's say it looks like this. It has its x component, which is in the x direction, and it has its y component, which is in the y direction. Because P is going from here to here, it must be going that way, and y's component must be going that way. Now to get the magnitude of P, we want the length of P, and hopefully you have spotted that it is the hypotenuse of a right angle made by its two individual components. So by Pythagoras' theorem, the magnitude of P is equal to x squared plus y squared, just like in Pythagoras' theorem, and then square rooted, again, just like in Pythagoras' theorem. So the magnitude of a vector is the square root of its x component squared plus its y component squared. Pause the video to get that copied down, please, and then I am going to run through an example. So for our example, we have a vector Q, which is 3, -4. We are going to find the magnitude of Q, first of all, 3Q, and -Q. So first off, the magnitude of Q is going to be the square root of 3 squared, the x component, plus -4 squared. Now in your books you should do this with a new equal sign on each line and not doing it in a string like I am. This is very bad notation, but I'm just doing this for space. So the magnitude of Q is 5. For part B, the magnitude of 3Q, we could multiply both of these by 3 and work it out that way, or we could recognise that 3 is a scalar. It's got nothing to do really with vectors, so we can take it outside of the magnitude sign. This vector 3Q is 3 times as long as Q. So if Q has length 5, 3Q must have length 3 times 5, which is 15. Finally, for part C, the magnitude of negative q. This is very similar to when we did the magnitude of negative 3. So if we look at the magnitude of the number negative 3, it is equal to 3. That is its size, that is its distance away from 0, which is the same as the magnitude of positive 3. This has size 3. Same thing happens with vectors. The magnitude of a negative vector is exactly the same as the magnitude of the same positive vector, because magnitude is just size and you can't have negative size. So the magnitude of negative q is the same as the magnitude of positive q, and we found that up here, so that is 5. That is everything you need to do exercise 1. Yeah, all of exercise 1. So you can pause the video here and do exercise 1, or you can continue to watch for exercise 2 and then do exercise 1 and 2 together. Our next example is a real life scenario. So a plane flies from point A 120 kilometers due north. Now in this type of question, just remember your compass. If it's due north, it means straight up. So we're starting from point A. Due north is going to be straight up like so. Then it flies due east to point C. So that means this is going to be a right angle. And we can label the distances. This is 120 kilometers and this is 80 kilometers. And that is part A done. For part B, we're going to write the vector AC as the sum of two column vectors, and we're going to find the resultant vector. So this is using what you learn in the adding and subtracting vectors lesson. Now, this means we're getting from A to C, but we have to use, like we did in the last 2 lessons, the moves that we have available. We can only go from A to B and then B to C. So if we want to do the vector A to C, we're going to have to go from A to B first, and then we're going to have to add on B to C. The vector A to B, it has no x component. It's not moving right or left, but it does have 120 in the positive y direction. B to C has 80 in the positive x direction, but it has no up or down, so it has 0 here. So when we add those 2 vectors together, the vector AC can be represented by the column vector 80, 120. For part C, we are finding this. Now this is the magnitude of the vector A to C. That would be the same as this distance here. So that would be a direct journey. If we made a direct journey from A to C, or let's say the plane had flown from A to B and then B to C, and then it just needed to get back to A, it would be this distance here. That is the magnitude of the vector AC. Now, the vector AC we've just found is 80, 120. So the magnitude of AC is what, Ramis? That is correct. It is the square root of the x component squared plus the y component squared. And if we put that into our calculator, we will get 144.222, and it's asked for the nearest kilometre, so we'll get 144 kilometres. That should now be enough for you to have a go at exercise 2. So have a go at those questions, and if you get stuck, please let me know and I will help you.